Dude.
All right, checking notes. Take a look at your bell work. Notice that there is no answer choices, so sig figs and units are important. I don't think so. Did you send it?
No. Rebar's restaurant was a bad game. They look like
Oh, yes. So I got your packets. I never got hers.
Didn't you know about corporate?
No, I did not see it. I don't know if it's referencing the angle is exerting.
One person already.
What's that?
Notes.
We're gonna learn about torque today.
Are they still
Torque? Yeah.
That's what that was.
Yeah.
Yes.
Remember that
Checking
check?
notes.
Yeah.
What
But
is it?
the answer?
The answer's torque.
What's torque?
Torque, nigga.
If the torque of a force about axis. Oh wait. The turning effect of a force.
I've been before cool. Notes, nigga.
Dude, what do you mean?
You guys lost by a lot.
Actually, have no clue. I haven't seen that word before.
Everyone's got notes.
Hey, look at that. Flip. Boom.
That's
Awesome.
Lauren, what time do you mom think you
Awesome.
Around
Alright, any more notes?
7:10.
Alright, I checked on notes. Going once, going twice.
I live 5 minutes away, so it's
Are they there? Okay.
I'm lucky.
I think I might have put them on my back.
How long do you spend on homework? Like, what's the class that you get the most homework?
So what?
Like, what's the class you get the most homework?
Let's take a look at our bell work here.
So far this class, yeah. But now my AP Euro, since I have to study for my Socratic seminar.
What is the nigga wearing on his back?
Okay, let's see here. Teams. Let's see.
I'm more
announcements.
It looks like he's
Starting
gonna.
tomorrow.
Not me.
Well, some of you guys.
Can I like?
I'm going. I'm sure
I'm just showing
you. Make sure to check the deets
I'm really
on the
stuck. I don't know
posted
what I'm
teams.
doing.
Okay. I posted a couple days ago with all of the wonderful info. Really, really important that you get here before the buses leave. Right? The buses are leaving at 5:30. You need to get here before 5:30. Let's shoot for 5:15. And if you happen to be late, message me so that I wait for you.
Don't show up.
If I don't hear from you and you're not here by 5:30, we will leave without you, and there will be weeping and gnashing of teeth. So, yes, Alexi. Yes, you can bring blankets on the bus. You can, at your own risk. This is what we always say. So, I mean, I don't care how big of a bag you bring on the bus. You can bring bags into the park. They'll have to be searched. And you can't bring bags with you in line on most of the coaster rides. So you'll have to pay for a locker if you want to do that, or just leave it with somebody who isn't riding. Yes, Christian. Back to Paxton at the evening. Between 10:30 and 11. Based on traffic and how long dinner takes.
Dinner.
Blankets? I mean, you can bring blankets.
I'm not going.
We should have outlets,
Are you going?
but there's no guarantee that they'll actually
I'm
work.
not going. Are you going?
But they should be. Yeah. Jordan.
How does the groups work for it?
Expectation.
Like how are we organized in groups, or is it just like?
So your groups, in terms of the lab, or just groups
Just in
roaming
general.
around the park?
Just in general.
In general, you can minimum size 3,
Those are selling.
but you can be in as big as group as you want. But the labs, they have to be 3 to 5 people per group for your lab.
And do we get like together at, like
Maybe it was like,
lunchtime or
oh,
like?
we got a toothbrush.
I'm not requiring you guys to check in with me at all during the park. So we get there at 10, I let you loose, you guys have your lab packets in your groups, and I'll occasionally see you guys around as we, hop around to the different rides.
Wait, so we're supposed to carry our lab packets around the whole park?
Yes. Until you're done, and so I may have some extra merchandise gift cards for those students who get their labs done early. So if you can find me with your completed lab, I might have a little prize for you.
Ooh. So,
You can do that, sure.
You still?
Yeah. Like, if you want to track me down, go for it.
Oh no, he got rid of the pieces. I think he'll put the.
Huh? The packets in the morning. So if you wanted to get a head start, you can get them like at breakfast. And you can work on them on the bus if you want. But there are a lot of things that you can't do until you get to the park. But there are some things like you can read over it, you can do like the preliminary questions. So you can definitely get a head start. Yes, thank you, Larry. Yes.
5 minutes later, do we really need to go this game? Oh, they want to go.
I will go look for that. Hey, Tracy. I'm sorry.
I feel like that's a
Guys,
catapult.
Tracy has gone in the last year, right? So Tracy has a good experience. Good? Okay, good experience that she would like to share when she went to Brook Gardens last year.
I mean, it's not like anything too much. It's kind of like what Mr. Raymond said. You're literally roaming around the park by yourself. I saw him like 3 times, and he was just on random rides the whole time. He would literally just be walking from one part and then he just pass Mr. Raymond. Oh, hey, Mr. Raymond. Hey. And he would just stay, but it was pretty fun. You can eat lunch whenever you want. You don't have to wait for anything or anything like that. They have I think it's this one spot over there. They have really good food. Like they have pulled pork and barbecue rub and all types of stuff, ribs and all types of stuff. I was like, oh, y'all get it. It's pretty fun. Y'all have fun, but don't let your work interfere with your fun. That was it. Have fun.
So did you take your paper with you like on rides? Like what did you do?
Oh no, he's nothing.
I have pocket. So I kind of folded my paper and put it in my pocket. But my friends, we got together and we just got one walkthrough and we kind of kept our stuff in there until we were done. And then we just took our stuff out because they were constantly roller coaster hopping. I mean, they would get on one ride and get back on. I think they went on like that tiger ride or whatever. No, it was cheetah one. They went on that one 13 different times. I kid you not. I sat down and took a nap. I woke up in there, it's still raining. I was like, oh, okay. But so we didn't have a chaperone, it's not a group. It was kind of just us. Oh,
What are you looking for?
It's not just
Nice.
other things.
Ah.
So when you're in line, it's not just gonna be your classmates, it's gonna be other families and other people that just go there. And I think also over there they also have an elementary school there. So it was little kids running around too. So it's not like Grad Bash necessarily where they close down the park for you guys. You're still dealing with other civilians. So you're still gonna be awake.
Guy bash was chaos. I would never go to Guy Bash.
I had fun. It was a cool experience.
You went to Guy Bash?
Am I going to Grad Bash? Oh, I mean I am, but that's a different.
I think about their 8th grade grad
No,
badge?
just offer grad.
That's what they're talking
I
about.
wasn't.
I didn't have that either.
So grad bash is basically
You don't
like,
want to go there, bro.
for seniors at least, grad bash is like when Universal, they close the park down for seniors.
Middle school grad.
And we're there.
They should have
Like,
everybody.
what,
Kids
like
were
3
hopping
o'clock
up.
was the rating?
Still two.
Doctors
Okay.
usually get
So, like,
the roller coaster was
like,
slow because you just hop off the red
Friday,
pool.
like
Everything
after,
gets stuck.
and then we're like
They
in the
just
park.
you can't exit.
And then we're like, it's like other high schools that are all over.
See, I get one of the New Year's Eve parties. People that New Year's Eve.
Yeah, Tracy, I don't know where they are. That's kind of disturbing. I mean, you guys were the only ones to mess with Loki. Put them on my desk. So far.
Jordan, did you do your calculations? Or did you copy?
Yeah.
I didn't do my notes last night and then
I don't even know what torque is, I don't know what newton is, I don't know what
I
fan
had to
is.
learn today.
I feel like most people get. I don't know anything, okay?
So, you can just
Oh, yeah.
do everything.
He's gonna kill me.
Try to find them. Because, yeah, I only have half of them as files.
Why is he wearing cap? That really gonna piss me off.
Wait, are y'all going to Busch Gardens?
Got exhibit on. And I got a game. So I'm gonna get it good.
Yep.
Oh, is that that? Yeah. Console. This is
Yeah.
How are you doing? I think your class is
Oh my god.
But you have like 30 minutes. You have like 30 minutes.
I like your hair.
40-ish to get breakfast because where we were at, there was a.
I just saw you, yes, 2 days
A
ago.
Waffle House.
You
McDonald's.
look big. You look
So
like
yeah,
you're-
what a lot of people did though, because like I'm just a lot of
Yo, imagine your cat playing the I won't lie. I checked my grade requirements. I'm missing. I checked my grade requirements. I'm missing. You're missing? No, I'm missing. No. Oh yeah, that's how if I went to a normal school, like a regular high school, I'll be done. I'll be done right now. I have enough high school credits.
Yeah, you just had to plug into the torque is equal to FR sine of theta. That's really all.
I know what that is.
Alright guys, sorry, we're trying to track down the stack of permission slips.
We can help.
Uh-oh. I turned in mine, right? Oh,
Guys, I'll turn them in, except for I'm still missing one from one honor student, which
Dang.
I haven't seen yet today.
they're on
So,
theta.
um,
Where's theta in this?
It'd be 9.
It is possible.
Eventually means it's just
But yeah, so
It'd be nice.
the idea was is that we would scan them so that I can access them on my phone if necessary, so that I didn't have to bring the paper stack with me to Busch Gardens. But
How you doing?
I only have half
Even if you wasn't in the class last
of the things scanned.
I remember that one where bro, we had like a lot of
Well, I mean, you turn it in, so you can still go. It's just, I need it in case you have to.
he went on that 73 and 9.
So,
2014, 2016 won.
anyway, let's take a look at our Bellward question.
Don't the Bulls have the most wins? No.
Alright, we got some answers. All the same numbers, but definitely different in the units. So I'm gonna call that done.
Wait,
And here we go.
Jordan, did you put NM? Okay.
I gotta take this off. This is
You want to die?
uncomfortable.
Why do you have it?
not evaluated, right? Were you at the game though?
Catapult.
Were you playing? I'll bet it. Kyler. Did you try out for JV? I better have a picture of myself. Bro.
Okay, so we're solving for torque here. If you look at your equation booklets here, we're in section A4. Okay, so at the top of the page, there's only one main equation for torque. So here it is. We've got our torque, which is given by the symbol tau. Actually, this is lowercase tau. We already learned about uppercase tau because that stands for period, which is the time for
One
Oscillation. Oscillation.
one oscillation. I think technically
Ovulation.
occurs in a set pattern as well.
I was thinking about something else.
So, I mean, technically, I wonder if that's where it came from.
It is.
I thought about
I looked it up.
Because,
I looked it up one time.
yeah, when you have your period, it's, yeah, so that's,
It's a
huh,
cycle.
look at that. See, you learn something new every day.
It's the circle of life.
It is the circle of life. And the depth of your internal structures.
It's shedding.
Yes, the
And
shedding.
and your rational thinking.
Yes. Some people call it dragon time.
Yeah.
I've heard that.
Shark weed.
Shark week, yeah, I've heard that too.
Ooh,
It's just like why?
we can get all
So,
into that. Oh,
Yes,
why?
but we're not going to. Let's go into physics. Here we go. All right, so we got our tau is equal to F times R times the sine of the angle here, where we've got our force and our R vectors. So R is kind of like the position, but when we talk about forces, and we're kind of go back and forth and compare torques with forces because we've learned a lot with forces. We know that forces control motion. So torques are kind of like forces in terms of torques control rotational motion. And we've talked a little bit about rotational and circular motion, but this next chapter, we're gonna finish it all out before we jump into something completely different, like electric charges and magnetic fields and all of that fun stuff, which is cool, yeah. But it's a lot different than the mechanics that we've been learning so far up to this point. So this is kind of like the last topic that we will actually need for the AP Physics 1 exam in May.
Oh no.
All of the rest of the things that we're learning this year is in preparation for next year, if you so choose to take IB Physics next year. But it's still part of the course, so you still have to do it. But it won't be tested on in May. Only all of the mechanics stuff is on the AP exam. Yes.
But what about physics 2? Does all stuff like feed into the same thing?
So most of the stuff, most of the additional things that we learn at the end of this year, as well as all of next year, most of that is on the AP Physics 2 exam. I don't make my IB students take the AP2, but it is an option if you want to take the AP2 exam. If you want that extra college credit chance, we allow the students to, but we just don't make you.
If
That's for
we're-
next year.
If we're not IB students,
You can still take it. Well, so technically, if you're not an IB track student, if you're just an AP student, but you want more physics, the next step would be to take IB Physics next year. Like you'll take it on the SL level, and you'll do all of the things that the IB students would do, like do the IA and do the collaborative science project. And you'll get a certificate for completing an IB course, but it doesn't lock you into the IB program at all. But that is the next step. There's also an AP Physics C class, which I have mentioned before, but we've already kind of wasted enough time today, and we'll talk more about possibilities for next year, maybe like February, because March, you'll actually have to choose your schedules or your classes for next year, and we'll talk more about that in great detail.
I'll visit you.
Cool. I'll take it. All right. I don't know how I got onto that tangent, but tangentially.
Tangent.
There you go.
Tangentially.
Yes.
I move around
So,
tangentially.
Yeah, I really don't know how I got there.
There's
So
no key.
the angle here is going to be the angle between the force and the position
Where the
vectors.
G
That's
is.
kind of how. Okay, so torque. Okay, so torque is basically a force that we're applying to cause a change in the rotation of an object. Okay, so like forces control the translational motion, as in motion through space, but torques will control rotation, as if we have an object being still, but it can spin. Okay, and then there are the possibility of having both happening at the same time, where we have equilibrium, which we'll talk about in a few, where both your forces and your torques may be balanced or not balanced. Okay, so so here we have we are trying to open a jar of pickles. I saw a reel one time where this woman she super glued a lid onto a jar of pickles, and then went to a gym and asked these really buff guys to try to open up her jar of pickles. It was fun because obviously they were trying really, really hard, and they're like, man, like I should do this, but of course, you know, it's a prank because it's been super glued. Anyway, so let's take a closer look here. So here's our lid of the jar of pickles, assuming that it's a top-down view. Okay, so we've got the radius here is 3.8 centimeters. Of course, we're going to have to convert that into meters, right, for any calculations. Absolutely. Now, so as we put our hand on the jar, imagine the last time you did this, which way would we turn it? Because there's two ways. We can either turn it to the left, causing a counterclockwise rotation, or we could turn it to the right, using a clockwise. Which one do we do to open it?
Counterclockwise.
Counterclockwise, okay? If you've heard the term righty-tighty, lefty-loosey, okay? That works as long as you're looking at the top of the circle. Okay, so righty-tighty, we're going to tighten it. We turn it clockwise, turn it left, lefty-loosey, and we're turning in a counterclockwise fashion. Okay, same thing happens if we're actually using screws. As we screw something into the wood, we turn it clockwise to go in, and then to screw it out, we turn counterclockwise to loosen and to get it out of the piece of wood. Still can't find them, huh? Can you, yeah, I really don't know where they went, which is kind of disturbing. Can you message Mackenzie and see maybe if she knows where they're at? Cool. Okay, so we are exerting a force tangentially, so we're going to assume that all of the points of contact that we would actually use as we grip the lid is focused just on one point. Okay, and since we are exerting it tangentially, that's going to be tangent to the circle as like that. So here's our force. Our force is what, 150 newtons, okay? So the R here, the R vector, this is going to be the lever arm, or the distance, the vector that connects the axis of rotation to the point of application of the force, okay? So, for example, like before, let's say we had a ball rolling or sliding across the floor, okay? Before, we would have drawn our forces as if they were all acting on the center of mass. And that was fine if we're just talking about forces. But if we're also talking about torques, the position of where the force acts on the object matters. So when we're talking about torque, okay, the force of gravity still is assessed at the center of the object, okay? But the force of friction, that occurs at the point of contact of the ball and the surface. So it's got to be drawn at the bottom of the ball, okay? So assuming that it's going this way at a certain speed, it's sliding here. So my force of friction has to be pointing left still, but drawn at the point that it actually acts, okay? Same thing with the normal force. The normal force is that upward force of the floor upward onto the ball. So it still points up, it's still just as big as it was before, but now it's going to be drawn where it actually applies. Okay, so as we do our torque problems, we're gonna draw our forces at the points that they're actually applying. Cool, okay? So that's why this is here. So our R vector is really just the radius of our circle here, okay? And I know this is a lot of intro to answer our question, but it's part of our lesson, okay? And I wanted to give you a good foundation before we move on and we use torque in other situations. Now, the only other thing is the sign of the angle. The angle is the angle between the force and the R vector here, okay? What's the angle between the force and the R vector here?
90.
90 degrees. What's the sine of 90? 1. It's 1. Yeah. So the sine of 90 is just 1. So if the force is perpendicular to the lever arm here, then our torque is really just F times R. Easy peasy. In this case it is. So our torque here is really just 150 newtons times 0.038 meters. And when I get my calculator here, I get, oh, it was just up here. I just erased it. 150 times 0.038 gives me 5.7 Newton meters. This is not newtons per meter because that's per means divide. This is Newton meters, okay? Big N for the Newton, small m for the meter. So let's take a look and see who got some points for our bell work question today. Yes. Stay.
Where's the joke of the day?
Oh, you're correct. Did I tell you the lizard in the bathroom joke
No.
last class?
I think so.
Oh wait, no, you told us the cabin. It's like the
Commode.
commode.
Yes, yes. Okay. So apparently I missed my 1A and my 2A there. All right, so let's go to our next one. Why do eggs like traveling?
They like classroom.
They like running.
What's that?
Yoki.
Because they are explorers.
Oh,
These jokes could have so much better answers, bro. Like, you're picking the dumbest answers for these.
Only eggs like to laugh because they love to crackle.
Okay,
Shut up.
here we go. So
I'll
go
take
back,
that
we'll
one.
assign you
I'll
your
take that
points. So it looks like we got up and at, spinning out mutants, maniacs, doing that point for the bell work here. Let's see, the spectrum gets a point, and up and Adams gets a point, Sarah gets a point.
It's close, guys.
Symphonic
What?
That's why I'm over
gals
here.
get a point.
She bought another idea, but I knew that it
Oh, almost, make sure that the end
That
is
happened.
lowercase, Nishan on that one.
No, I didn't.
And apparently you just didn't put on your units at all, so, there we go. All right, very good. So let's continue, let's jump right into our next challenge question here.
I can't do this no more.
I'm so sorry.
No, you're not dead. You're alive.
I apologize.
How do you do this? I don't like how my calculus lessons are just glossing right over each other.
Calculator. I need calculator now. Give me.
Oh, I found him, Tracy. Is she still in here?
Her name's Tracy. That's so cute.
Where were they?
Oh, I was talking about her name.
In my black
She's
thing.
cute too.
Although technically, I think she looked in there and she couldn't find it, so I don't feel too bad.
Oh. Sound like my mom feels a snake it would have bit you. It was a gun
There's
you
a
would
snake
shot
in
you.
my boots.
If it was a gun
Quick, who said that?
shot.
Woody.
Woody.
There you go. You guys got it.
Wait, how do you?
So
delete?
yeah, which
What's an
angle
R?
do we
You
use?
delete.
I don't know.
It's
Hopefully you choose
8
the right
right?
one.
It's 47 degrees.
How are y'all
Wait.
figuring this out?
It doesn't work.
Babes?
Again, sig figs and units are important because
Not all
there's
of
no
it.
choices.
You can scroll back up.
Wait a minute.
Where is it?
This is confusing.
You gotta learn how to use
Wait,
Big Mama.
which
What
one?
kind of-
Big Mama.
What are you trying to do?
Big Mama.
It's R18.
use this equation. Just plug it in.
R18.
First answer.
It's
Well,
R18.
2F
F is 8.
2 times.
R is 0.18.
I got 40.
What mode do
Sine.
you have your calculators in? Degrees. Might make a difference. It didn't last time because the sine of 90 is just 1. But this time,
Sine of what? I have mine in degrees
47.
mode.
Bro, how the
I got 48.
what did I get?
21. 2.1. 2.1.
go in mode. Should be the third one down.
Degrees radians?
Repeat?
Degrees radians?
Degrees.
That's what
Okay,
happened.
so
Yes.
we use this formula.
C's get degrees.
Oh, exchange
That's
it.
what they say.
Use this formula.
Where's Bella?
So we use 2 times 8 times point.
Where in the hell did it 2? Where the hell? Martin.
Martin, where the fuck you get
Where the
point
fuck
one
did
eight?
where did we get 2 from?
Because there's.
They're all here. They're all
Are
here.
there 2 forces?
Oh,
No, we're just using 1. You should ask which angle we use.
yeah.
Oh, then just divide by 2 and.
Bro,
Wow, we
what?
got
how did we get
some
this?
different numbers here.
Martin, what did you do?
Explain this, we're applying 8 newtons to it.
I'm not doing it.
We're applying 8 newtons.
Let's go family exam. I don't give a fuck. This is one credit I just won't get.
Martin, what is R? Is R 18?
R is radius.
Yes, I know. The radius 18.
How is the radius 18?
Because that's what it's saying it is.
That doesn't make sense.
That doesn't look like it's
They
halfway.
were,
A circle
they
either
were like,
way.
It doesn't.
So how the fuck is
they were that.
18?
Can
Oh.
someone please open the fucking radius? I swear, ask the question so many fucking times now. Martin.
Martin is locked in.
What is the radius?
Alright guys, I got calls done. 5.
Thank you, thank you. I actually hate you so much. You piss me off.
Dos.
Right here.
Uno.
Okay, so it was wrong.
There we go.
No, yeah, you just had
Alright,
to
here
divide
we
by 2. I thought
So,
this, the arrow on the
we've got
bottom.
our FR sine theta. It's obvious that our force is 8 newtons, that our R is 18 centimeters, but 0.18 meters. That's how we're going to convert. And the real question is, well, which angle are we going to use? So remember, this is the angle between the force and the R vectors. And keep in mind, we can slide these things around a bit, okay? So if our R vector has to be drawn from the axis of rotation, which would be where our nut is at the bottom left hand of the screen. So the R is pointing up and pointing to the point of application. So if we just slide it along, then that is our correct answer, or our correct angle here. So 47 degrees, so we got 8 times 0.8 times the sine of 47 degrees gives us, let's see here,
1.05, I think.
8 times 0.18 times the sine of 47 gives me 1.05, but let's check out sig figs. 8 only has 1. So the correct answer is 1 Newton meter. 1 Newton meter.
So everything
Yeah, if you happen to round to 2 sig figs accidentally, technically, according to all of the IB and AP grading, if you're off by 1 sig fig, you still get full credit.
No.
Okay?
That's sweet.
I
So, did we have? Oh, sorry, Jordan.
Dude, I was locked in.
Oh,
Technically, I got the answer.
Sometimes I
got
just do
answer
it
too.
just to see if maybe you'll like you wouldn't catch
Alright,
it.
so there's no perfect answers. There's not even the 1.1 answers. So we'll have to go. The next best option is 1.05 Newton meters.
I got the answer.
So I know we have some of those. Let's take a look.
I got the answer.
Let's take a look.
Let me see, buddy.
I thought I was doing it wrong.
So
Yeah, sure.
first
Sure.
is
I'm not sure.
first place. Good job. Let's
not
see
much.
the next one.
I just
Second
watch
one.
it with conditioners. I have to do it every day since
And looks like Quantum claims that
it
third
dries
place.
my hair
I
out.
can't wait for
Yes.
And
Very
I
good.
it's this conditioner like near my wrist,
All right.
and then another oil for my scalp.
Okay.
This
So
curly hair
let's
right
go back.
on the end.
Let's talk some more concept stuff. So torque.
Thanks.
If you remember when we talked about work, okay? Work was equal to F times S times the cosine of the angle. Doesn't it look a lot similar?
No, not really.
In fact, well, S is displacement. R is going to be that distance from the axis to the point of application. Both of them would be in meters, okay? So we've got a force times some sort of distance times either a sine or cosine, okay? So, and I might have mentioned before that the work was actually a way to multiply two vectors together, because we actually have the force, which is a vector, and my displacement, which is a vector, but we're going to multiply them in a special way. This is called dot product, aka scalar product, which means that it gives us a scalar answer. When we talked about work wasn't a vector, it didn't have a direction, so it was a scalar version. We don't need to know exactly how to do that. If you ever take AP Physics C or a calculus-based course in college, you'll learn about what actually is the dot product. And up here for the torque is going to be the cross or the vector product. Basically, two different ways to multiply vectors that give us either a scalar answer, work, or a vector answer, torque. So they're very closely connected, but that's about all that we need to know about that. I'm not going to go into great detail because it's really not a part of the course. It's not in the IB stuff either. It's only like calculus-based stuff that we actually learn that. Not that it's actually, you need calculus for it, but it's just not in the AP Physics 1 or 2 or the IB stuff, okay? So, but it is important that torque that we know is a vector, which means it has a direction. So let's talk about that real quick, okay? So, the direction of the torque, if we were to look at something rotating in a plane, whether it be the plane of the board, or if you have a test,
Bless
thank
you.
you, like a test paper, then it's going to be the plane of the paper that the object is rotating in, if you look at it, okay? So the torque is going to be perpendicular to the plane of rotation, which means that if this is the X and Y plane, torque is going to exist in the Z direction. Okay, so three-dimensional, perpendicular to the plane of the board, it's going to be pointing out of the board towards you or into the board away from you. Okay, so there are some sign conventions that we learn here in physics that talk about three-dimensional directions like this. Okay, so when we say out of the page or out of the board, it's going to have a dot for the symbol. Okay, that's what that means. And then into the page or into the board, it's going to have an X. And here's a good way to remember which one is which. Imagine you're shooting bow and arrow. Okay, so as you shoot a bow and arrow and you let it go, as you watch it, you're watching the feathers as they go away from you. See the feathers? It goes away from you into the page. If an arrow is shot towards you, you see the point, because it's coming out of the page towards you. Okay, so into the page is the X, you see the feathers. Out of the page is the point, you see the point of the arrow. Okay, so again, it's just a sign convention. We'll actually use this when we get into fields, because we'll also be dealing with three-dimensional directions when we talk about electric and magnetic fields, which is going to be sometime this spring. Okay, cool. All right, so torque not only is going to be into and out of our page, but we also have to say, okay, well, is it positive or negative, right? So remember when we talked about rotating and the angles, if we were to be going in a counterclockwise fashion and we look at the angles are increasing in value because they're measured by measuring up from the positive x-axis. So if we have a counterclockwise rotation, that angular displacement is positive, so the angular velocity is positive, the torque is positive if it causes counterclockwise rotation. and vice versa. So if we're going in the opposite direction, if we're going clockwise, the angles are decreasing in number, which means that my torque is negative. So a torque that causes a clockwise rotation, we call that negative torque, and then a torque causing counterclockwise, we call positive. And then we also know where in space it will act as well, okay? And it kind of goes back to the whole screw, like what happens with your screw. As you screw a screw into a piece of wood, you're turning it in a counterclockwise fashion. And what happens to the screw, it's going into the page. It's going into the board as you turn it in a clockwise fashion. So torque that's negative is going to be into the page. The torque that's positive is going to be out of the page. As we turn counterclockwise to loosen that screw, the screw comes out of the wood. It comes out towards you. So it works. It's the same kind of concept here. Okay, all right. Some other concepts with our torque. So we've got our force. Naturally, the more force we have, the bigger torque we're going to have. Okay. The R and the angle is kind of tricky. So let's go to the door. Well, I'm going to the door. You can follow me with your eyes. Okay. So I want to get out of this door, so I need to push it open, right? Didn't work.
We're trapped.
What needs to happen?
Handle.
I need to unlock it first, right? Okay.
Unlock.
So the handle, I need to push on it, right? That didn't work.
You push down
Oh, I need to push down? Okay.
on the outside of the handle.
I'm pushing down though.
On the
That's the
outside of the
inside of the
handle.
handle.
Push harder. If you push harder, it'll work.
I'm just kidding. But yeah, so just because we're applying force, right, its position matters, right? Where I apply my force matters. Because so right now, notice that if I do it correctly, because I know how to open a door, right? So I see that this is the axis of rotation right here. So if I push down, or up rather, it doesn't matter where I push, if I push on the axis, what's the torque that I'm doing?
0.
No, exactly. If my force is pushing on the axis itself, what's the value for R?
0.
It's 0, because R is defined as the distance between the axis of rotation and the point of application. If the force is on the axis, the R is 0, and I get no torque. Okay, so obviously that's not how I open this door. Okay, so if I were to scoot over just a bit, having a small R, and I push it down, I can get it to go, but it takes a lot of force. Okay, it takes a certain amount of torque to make this unlock. I have to twist it, making a certain amount of torque, changing the rotational motion of the handle. Okay, so if I have a small R, I have to push with a good amount of force to make it open. As I increase my R, it gets easier. I don't have to push with as much force. And then if I push over here, ooh, that's easy. I can do that all day. Okay? Now, so the bigger the R is, the more torque I can get based on a certain amount of force. Okay? Just like if you ever have to change a flat tire, right? You get a flat tire, there's a nail in your tire, you stop, you jack it up, and if you've never changed a tire, if you've never learned how to change your car tire, that is definitely an important skill that I can teach you, not today, but we can definitely go outside someday and I can teach you how to change a tire.
Thank you.
Right? Because it's an important skill, plus it is full of physics, right? But so before you jack it up though, you've got to loosen your lug nuts. Okay, you can't loosen them when it's already up. Okay, you've got to loosen them when it's making contact with the ground because the wheel's going to spin if you try to take your lug nuts off when it's in the air, okay? Which we'll also talk about in a future lesson. That's a concept of angular momentum, but we'll talk about that later. So, if you take your lug nut wrench, that little, thing that fits onto your lug nut, it looks like a, looks like a crowbar or some piece of metal, and the idea is that you're trying to loosen that lug nut. So you're going to try to turn it. I did see one charger look at that front table next to
My lady friend.
It's wrong. It's alright. I still haven't fixed it.
By
It's been
12 minutes.
off all day, but each time I think about it, I'm busy. Or I don't think about it. Anyway, bye, Mercury. She's got fans apparently.
No one heard. It's
Huh?
wrong.
She's your majorette bestie. Nice. Okay, cool. What was I talking about? Oh yeah, so changing car tire, we've got the lug nut wrench, but it might be a bit difficult to actually get those lug nuts loose, especially if the last person to put a wheel on is like the shop. They really crank those suckers down because they don't want your wheel to fall off, obviously. So you may need to like stand on it, like put your full weight on the edge, because as we increase our R, we're going to increase our torque. But even then, some of us are, petite, okay? And you may not even if you jump on the tire iron, you still may not get it to budge, okay? So your next best bet is if you have an iron pipe. Okay, that fits over the tire iron, effectively increasing the length of that thing. And as you increase your R, you're going to increase the torque from the maximum amount of force that you can apply by standing on it, and then you can get those things loose. So it is always a good idea to have an iron pipe in your car that'll help you increase that length of your tire iron, especially if you don't weigh as much and you don't have the strength to actually crank those open or crank those loose as well. Okay? So we've talked about R, we talked about F, the sign of the angles. So the angle, so right now I'm pushing at a perpendicular angle, right? Because the R points this way, I'm pointing straight down, so I'm maximizing my torque here, okay? But then if I decrease my angle, if it's less than 90 degrees, I can still open it, but I have to push with more force, okay, to get the same amount of torque. And as I increase, or rather decrease, my angle here, it becomes harder and harder. And if I push directly against the R vector, so my force is either aligned, it's pointing with it, so the angle is 0, or it's exactly opposite, where the angle is 180 degrees. In both cases, the sine of 0 and the sine of 180 is what?
0.
Is 0.
Let's go.
So
I didn't know that.
forces acting with or exactly against the R vector do no torque. Which is why I can push as hard as I can, and I'm still not going to make that thing move if I push directly against it. Okay, so we've talked about that to completion. Have you ever noticed, though, that the handle of the door is always on the opposite side of the hinges? So, like, if we open this door, the hinge is on this side, right? Okay. Don't put your fingers in there, all right? So, as we open it now, naturally, we don't think much of it, we just twist and go, because we're used to it, okay? But what if the handle was in the middle of the door? It would be harder. Why? Because there's less R. So if I were to unlock it, I'm not pushing with this hand, but I'm just pushing here. It's harder. You might find some older houses have the doorknob in the middle of the door. Yeah.
My grandma's
Weird.
house.
Okay. So what I would do is I would unlock it, I would twist it, but then push on the outside side. Okay. If you remember, if you've ever seen the first Jurassic Park movie, okay, at the end of the movie, I'm not going to spoil it, but at the end, so Dr. Grant and Dr. Sadler and the two kids are in the control room. Power's out, the doors won't lock because they're electric, okay? And the raptors are trying to get in. And so the door actually swings in. So Dr. Grant comes over here and pushes against the door. And so his girlfriend comes and pushes right next to him, okay? So Dr. Grant is closest to where it opens, where the raptors are trying to get in, which is furthest away from the hinge. Assuming that they're exerting the same force, who's doing more torque, Grant or Sadler?
Grant.
Grant is, yeah, because his R is greater. So although both of them are exerting the same force, maybe, he's exerting more torque. His force is doing more work to keep the raptors out than she is. Not necessarily because she's a woman, but just because she is closer to the axis.
He said it. We did not say anything.
Actually, there is a scene where John Hammond is talking with Dr. Sadler, and Dr. Sadler is going to go and rescue the kids and Alan. And John Hammond's like, well, I should go. And so they have this brief thing about, just because I'm a woman doesn't mean that I can't get the job done. So it's a little bit of, touching on that aspect. All right, so I think that's about it for that. Conceptually, there's a couple more things that I want to mention, and then we'll be done. Okay? There we go. The seesaw. Oh no. Oh yes. The seesaw. So, we know that forces cause accelerations and torques cause angular accelerations. We'll talk more about that in future lessons, okay? But let's take the equilibrium side of things. So in equilibrium, if an object is at rest or moving at a constant speed, then we know that their forces are balanced. F net is 0, okay? Same thing happens with torque, okay? If the torques are 0, if there's more than one, and they happen to cancel out, then the object will be in rotational equilibrium, as in not spinning, or if it is spinning, it's spinning at a constant rate. Okay, cool. So for a seesaw, okay, here's a seesaw. Basically, it's a piece of wood. There's a fulcrum, some sort of support there. And we've got two kids, kid 1 and kid 2. Okay, let's say they're different masses, so they're going to be at different positions on our seesaw. So the idea here is we want the seesaw to be balanced, okay? So it's going to be at rest, and it's not going to be spinning. So we've got equilibrium in both cases. So equilibrium from the force perspective means that the sum of my forces has to be 0. Well, let's take a look at our forces, okay? What forces are acting on, so my system is going to be the beam of wood, the seesaw itself. So we've got kid 1 pushing down, so with their weight, so let's just call it FG1. Kid 2 pushes down there at FG2. The seesaw itself has weight, okay? And we always assess the weight vector at the midpoint of the object, so right in the middle. So so let's call this FG beam, because it's a beam of wood, okay? Or metal, it doesn't matter. So in order for this to be balanced though, if I've got some down forces, I have to have at least one up force, right? Yeah. And what provides that?
The middle part.
The middle part, the fulcrum, okay? Which gives us the normal force. So we know that, well, there's only one force pointing up, so that one up force has to be equal to the 3 down forces if this thing is going to be at rest, which of course it is. So I can say that my Fn, because my forces have to be balanced, then my one up force has to be equal to the combination of all of my downward forces. Fg1 plus Fgb plus Fg2. Easy peasy. But the torques have to be balanced as well, okay? Because this is in total equilibrium, both translational equilibrium, so not moving through space, but it's also not rotating as well. So it's also rotational equilibrium too, all right? Now, we've got to choose, just like we had to choose the reference level when we talked about potential energy, we have to choose the axis of rotation. And it could make logical sense to do so, or not necessarily, okay? In fact, I could choose any point to be the axis. It doesn't have to make sense. Like, I could choose that to be my axis. And then I would have to draw my R vectors to the different application force positions, okay? But knowing what we know about where I put my finger, and somewhere my torques are 0, right? Okay, so wherever there's a force, if there's a force acting on the axis of rotation, that torque is 0. So if I put my axis here, the torque due to that guy is 0. And I have less to calculate. But let's go a step further. Let's work smarter, not harder, okay? I want to find, how can I cancel out the most amount of forces? Where do you think I should put my axis?
Middle.
In the middle, where there's 2 forces. Absolutely. So I'm going to use a little circle arrow to indicate this is my axis that I've chosen, okay? So the torques due to Fn and Fgb are both 0. I don't have to calculate them. Cool. So now notice that there's only 2. And they have to be balanced, right? Because the net torque has to be 0 as well, okay? And we talked before about there's a direction, right? So what kind of torque, positive or negative, will 1 cause?
Negative.
If it were free to just move just by itself, like, so ignoring 2, look at what's going to happen if 1 is allowed to make things rotate. Which direction would it spin? Okay, so 1
negative.
pushes down. Here's the axis, so it's going to go like this in a counterclockwise, which means that the torque is
Positive.
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 Good, good. So I can say that my torque due to 1 is going to be a positive torque because it causes the object to rotate in a counterclockwise fashion. What about 2? 2 pushes down. Here's the axis. So it's going to try to move things in a clockwise fashion, which means that the torque due to 2 is going to be negative. Yeah, there you go. So see how we've identified that there's a balance here. And again, assuming that this is an equilibrium, and we only have 2 torques and they are opposite directions, they have to be equal to each other. So our torque due to 1 must be equal to the torque 2. Cool. Now, to kind of break it down with the equation, torque is equal to Fr times the sine of the angle. So as I draw my position vectors here, okay, so this is my axis, so this is where the start of my R vector is. So I'm going to start here, and I'm going to go to where 1 points. So this is going to be R1, however long that is. Okay? Same thing for 2. Starting at the axis that I chose, I'm going to draw my R2. Like that. Okay? All right. So, and can I assume that these are perpendicular to each other, the R and F here?
Yeah.
Yeah, I can. Sometimes we cannot assume that. Like, if we ever have a ladder problem, where the force of gravity points down, and my axis, let's say we choose it here, here's my r vector, those are obviously not at a right angle. So I'm gonna have to find what angle it is and use my sine portion as well, okay? All right, but let's get back to the easier example. So assuming that these are perpendicular, the torque is just r times f. Easy peasy. So then, so this is just gonna be FG1 times R1 is equal to FG2 times R2.
Number 2.
Here's the question. If the kids are the same mass, what would that mean about their distances?
Counterclockwise going this way.
They'd have to
If
be
the
equal
force is
in order
going
for
down
this to
equal.
remain
They would have to be the same as well. Yeah.
Okay.
Because, check it out, the force times the distance on one side has to be equal to the force times distance on the other side. So if they're the same mass, same weight, the r's have to be the same as well. Okay, so like they both have to be at the end, or they both have to be at the same distance from the end or from the middle, whichever way you want to cut it. Okay? But if they're not, where does the heavier one have to be to balance it out?
Close to the middle.
Close to the axis point.
Closer to the axis of rotation?
Yes.
Okay, so if the FG1 is larger, and you're saying that R1 has to be smaller, would that yield the same result if we have a smaller FG2 and a larger R2? I think it would. Yeah, that makes sense. So the heavier, so like if I go and I take one of my little kids, my big kids are just as big as I am, so I'm gonna take one of my little kids to the park, we're gonna get on a seesaw, I'm gonna be heavier, okay? So I have to slide towards the axis more than they do. They could be at the end to maximize their torque, but in order for me to balance it out, I have to reduce my R. I have to scoot in closer to the center in order for us to be balanced. Cool. All right, very good. Any questions? All right. I know it's a little late in the class, but we still have a good amount of time, so feel free to take 5 if you need. We've got our pods. If you did not finish your lab from last class, that is officially due at the end of class as well. All right, let's get started. The quiz is already up in focus. If you're one of those who just likes to jump in the quiz,
No.
first thing,
I
go
looked
for
at
it.
it and then I tried it and then I got to like E and I was